This video goes over the problems in practice number 2 for topic 1.1c. So let's get started. Problem number 1. The kilowatt hour is approximately equal to how many joules? Well, this is really a units question, and so I'm going to pull out my units table here and show you something. We have the watt here is an SI standard unit, and kilo is a prefix to the watt, which is SI standard. However, the hour is a unit of time, and we can't use the hour. You see, in SI units, time needs to be represented with the second. And so we'll need to convert first into SI standard units by going from kilowatt hours, the kilowatt hour, that's like 1 kilowatt hour. How many kilowatt seconds is that? So let's get going with that. Might start out with this idea that 1 kilowatt hour is exactly equal to, well, a kilo stands for 10 to the positive 3. So this is equal to 1 times 10 to the positive 3 watts times hours. Where I can say this because these kilo and this times 10 to the positive 3 are the exact same thing. So 1 kilowatt hour. All right. And I want to convert 1 kilowatt hour to how many kilowatt seconds is that? So I'm going to say is equal to how many, I guess, watt times seconds, right? 1,000 watts times hours is equal to how many watts times seconds? All right, let's go. So 1 times 10 to the third, that is 1,000, or I can leave it 1 times 10 to the third. Watts times hours. And I'm going to convert this by using the well-chosen 1 method, where I'm going to multiply it by a fraction that's equal to 1 because the numerator and the denominator are equal. And I want that fraction to cancel out hours. You see, I want to cancel hours and I want to get into seconds. However, in order to use an equality like this, I have to understand 1 hour is equal to how many seconds, and I don't know that off the top of my head, but I do know this. I do know, so that won't work for me. I do know that 1 hour is equal to 60 minutes. And then I can take one more step because I know that 1 minute is equal to 60 seconds. So what I can do is I can use these two equalities, this one and this one, in order to move from hours into seconds. First, I want to cancel hours and get into minutes. In order to do that, I'm going to take this equality, I'm going to break it in half. Half of it is going to go on the top and half of it on the bottom of this fraction. The way I decide which one goes where is I want to cancel this hours, which essentially is like in the numerator. And in order to cancel hours in the numerator, I need hours in the denominator. So I'm going to take and put this 1 hour, I'm going to stick it in the denominator, and this 60 minutes, I'm going to stick it in the numerator of my fraction. And this way my fraction will equal 1. The top and the bottom will be equal. So I have 1 hour on the bottom, and I have 60 minutes on the top. And this will allow me to say that this hour here and this hour here will cancel. And right now my units would be watts times minutes, but I don't want watts times minutes. I want to do again the same thing with this equality. I want to put the minutes on the bottom to cancel this minutes on the top. So I have 1 minute on the bottom, 60 seconds on the top, and again I can cancel. This minute on the bottom cancels this minute on the top. And this is what I want. Here's where I at. I have 1,000 times 60 times 60, which is 3,600,000. I think that's right. On the top for units, I have watts times seconds. On the bottom, I have 1 times 1 times 1. Sure, that's right. And what I end up with is 3.6 times 10 to the 6th. I could write it. That's 3.6 million. Watts times seconds. Now, I don't know that watts times seconds is a joule. I can assume that my answer is going to be in joules and standard units because all of these answers are in joules. But let's verify that. Is a watt times a second a joule? Well, 1 watt times second is equal to 1 joule. Is that true? All right, well, what's a watt? Well, we can see that a watt is equal to a kilogram meter squared per second to the third. So 1 watt times second is 1 kilogram meter squared per second to the third times a second. Oops, I almost forgot about that, right? Because this is what a watt is equal to, and this is what a second is. So that's a watt times a second. And that's, now we have to look up what a joule is. Well, a joule is equal to a kilogram meter squared per second squared. So 1 joule is equal to 1 kilogram meter squared per second squared. And maybe now we can see that this is going to work out. You see, on the left-hand side, I have kilogram meter squared, seconds, 3 seconds on the bottom, times a second, right? So maybe if I write it out just to be clear, kilogram meters times meters over seconds times seconds times seconds in the bottom times seconds is equal to kilogram meters times meters over seconds times seconds. And we can see that this is going to cancel here. Right, so we do have the same thing. We have, oh, I'm working off your page here. We do have the same thing. We have on this side kilogram meter squared per second squared, and on this side kilogram meter squared per second squared. So 1 watt second is equal to 1 joule. So that is to say that if my answer is 3.6 times 10 to the 6 watt seconds, I can replace this watt seconds with the joule and say that my answer then becomes 3.6 times 10 to the 6 joules. And that is what 1 kilowatt hour is equal to. This puts it on your sheet is answer number D, 3.6 times 10 to the 6 joules. All right, let's take a look at number 2. 2 has a graph. It says, the graph on the right shows the variation of displacement. So this is displacement on the x-axis of our graph. With the force F applied to an object, so this is force in units of newtons. It says the work done is what? So we need to find work. So this is a common thing that IB likes to do. They like to give you a question where work is not one of the things listed on your graph and ask you to find work, or some other quantity is not listed on your graph, but they ask you to find it. And there's 2 strategies that we use in this situation to get information from a graph that is not given directly. One is by finding the slope or the gradient of the graph, and the other is by finding the area under the graph. In order to decide which of these 2 strategies we're going to use, we use the units in order to figure out what that would be. So here's the story. If I look at this graph, I can see that my slope is going to be in units. Well, find slope, you pick 2 points on the curve, like maybe here and here, and you say, what is the rise and what is the run, right? So we say, between these 2 points, there's some amount of rise and there's some amount of run. and the rise divided by the run is going to give me my slope. Well, if that's true, then we can say that the units of rise divided by the units of run. So if my rise in this case, let's say, looks like it goes up 1, 2, 3 newtons, and my run is some number, maybe like 1 times 10 to the negative 2 meters, I'm going to end up with units of rise, that's newtons, divided by run units, which in this case is meters. So let's take a look at that. So for number 2, slope, which we call the gradient, would have units of rise divided by run, and that would be units of my rise is measured in this direction, it's some number of newtons, and my run is measured in this direction, it's some number of meters. So this is going to be rise units over run gives me some number of newtons divided by meters. I can figure out what that is equal to, a newton divided by a meter, because I know what a newton is. So I'm going to take out my handy dandy units chart, take a look at newton, and see that a newton is equal to a kilogram meter per second squared. So that a newton is really equal to a kilogram meter over a second squared. And a newton divided by a meter is this divided by meters. I can cancel meters and meters and say that the slope of my graph, the units of slope, which I could represent this way, it would be equal to kilograms divided by seconds squared, or kilograms times seconds to the negative 2 power. All right. Well, the problem asked me to find the work done, and so the question is that a unit of work, a kilogram divided by a second squared? Let's take a look. Work has units that are the joule, and it's equal to a kilogram times a meter squared divided by a second squared. So it's not a fit. You know, this is like the Cinderella story, right? It's like, this is not a unit of work. It needs a meter squared in there. It doesn't have it. So there's one other way that SI could expect you to pull information from a graph that it isn't immediately obvious, and that's by using not the slope. Slope is our first guess, but our second guess is by using the area under the curve. All right, well, if we look at our graph, the area under this curve is essentially, no great color, but essentially that area there. And we could take a look at what the units of this area would be. Well, this area is made up of blocks, some number of blocks. Let's just take a look at what one of these blocks looks like. Well, let's look at this block here. I have a block here, and if I wanted to find the area of that block, I would say that it has some kind of a height and some kind of a width, and base times height would give me the area. And the base of this is going to be measured in these units here, which are meters. So this base is going to have units of meters, and the height of this is going to have units of, well, this is 1 newton. So the height of this is going to have units of newtons. And so the area of this square is going to have, it's going to be, measuring, I'm going to multiply some number of newtons and some number of meters. So my units of area so I'm going to have some number of newtons times some number of meters, and that's a newton times a meter. Well, what is a Newton? Well, we just looked it up. It's a kilogram times a meter over a second squared times a meter is going to give me a kilogram times a meter squared divided by a second squared, or kilogram meter squared times seconds to the negative 2. And the question is then, is this units of work? Well, let's take out our sheet. Work has units of kilogram meter squared per second squared, and that's what we have here, kilogram meter squared per second squared. So you can see that this area would give us the right units, and therefore this is how we're going to find our answer. If it gives us the right units, it is the right strategy. So now we need this yellow area, the entire area underneath this curve, and there's a couple different ways you could do it. You could count up how many squares like this there are underneath this square, and maybe you say, like, you know, this portion and this portion kind of add up to one square, and this and add up to one square. Or you can use the formula for the area of a triangle. That's 1/2 times the base times the height, and that's what I'm going to do. I'm going to say that the area of this triangle is, I have a triangle that looks to have units like this, or a size like this. It's got a base that is 2 times 10 to the negative 2 meters wide. 2 times 10 to the negative 2 meters wide. And a height that is, I guess that's 5 newtons tall. And a height that is 5 newtons tall. And so the area of my triangle is 1/2 times the base times the height, which is going to give me 0.5 times 2 times 10 to the negative 2 meters times 5 newtons. We already checked to make sure that those units are going to work out for us. So we have 1/2 times 2/100 times 5, and we should end up with 5 times 10 to the negative 2 joules. Let's take a look. Yep. This is choice C, 5 times 10 to the negative 2 joules. Next up. Problem number 3 says, what is the ratio of diameter of a nucleus to the diameter of an atom? This is something that you're not expected to memorize, at least not at this point, and we have a table that's on activity 1.1c that tells us that the diameter of a nucleus is about 10 to the negative 15. Is it 10 to the negative 15 meters? And the diameter of an atom is 10 to the negative 10. And so divide these two, we get 10 to the negative 5 as the ratio. So choice C, 10 to the negative 5. And again, these values are pulled right off of activity 1.1c. Next up. Problem number 4 says the variation with time t of the speed velocity v of a car moving along a straight road is shown below. Which area or combination of area represent the total distance moved by the car during the time that its speed is reducing? Well, this kind of comes back to the same idea that in our graph here we have a velocity along the y-axis and a time along the x-axis, and that the area then under the curve would have units of these little squares that are inside this graph, or squares that have a height in meters per second. That's the unit of velocity. Velocity is in meters per second. And a base in units of time, which is seconds. Time is in seconds. So in this graph, each little square inside this graph would have measurements of some number of seconds and some number of meters per second. And when we multiply meters per second, so the area would equal units of meters per second times units of seconds, base times height, we would get units of meters. So that would be the distance. All right. Now, which of these areas represent time that the speed is reducing? Well, in order for the speed to be reducing, right, this velocity has to be going down. So we would say, well, in this time period here, the velocity is reducing. So this area would count. As well as here the velocity is staying constant, but in this time, the velocity is also going down, right? It starts at some velocity here, it looks like, and by the end of this time, it's gone down to a velocity of 0. So we would say that these two areas represent the total distance, right? Because the area under this curve is distance, where the speed is reducing. So we would say that this looks like choice C, S1 and S3. On to number 5. The graph below shows the variation with time of the acceleration a of a spaceship. The spaceship's at rest at t0. The shaded area represents what? So the area underneath this curve, really we ask ourselves, well, if we want to know what this area represents, we just have to figure out what units would that area have. So let's take a look at a box that would take place under here and say, well, what are the units of this box's height and what are the units of this box's base, so to say. And the height is going to have units of a, which is the acceleration, and those units are going to be, well, units of acceleration, meters per second squared. So this is going to have some number of, some units of meters per second squared. And the base is measuring time, which is going to have some units of seconds. So here we have units of seconds. The area, in that case, is going to have units of, well, area is equal to the base times the height of this square, right? If we want to find the area of that square. And that's going to be the base, seconds, units of seconds, times the height is going to be in some number of meters per second squared, times meters per second squared. We can write it this way maybe, and say, well, this second here is going to cancel one of these seconds here. And so that our area would represent meters divided by seconds, or meters times seconds to the negative 1 power. What is that? What is a meter divided by a second? Well, let's look for that. So we're looking for meters times seconds to the negative 1. I'm scanning through these SI fundamental units, and I find it right here. And know that that unit can only represent a velocity. So, in this problem, we would say that velocity and speed are about the same thing. We'll learn the slight difference between them in just a little bit, but that would represent the speed of the spaceship at t is equal to capital T, right? At the point when t is equal to capital T, that's when t goes from 0 all the way to capital T. And over that entire period, the area under this curve in that entire time period from t equals 0 to lowercase t is equal to capital T, that area represents the velocity or the speed. right? So choice C. Next. A constant force of magnitude F acts on a body. The graph shows the variation with time t of the momentum p of the body. The magnitude of the force F is what? Well, in order to find the force, we need to decide, are we going to use the area underneath this curve, or are we going to use the gradient? That's the big question that we ask ourselves. So let's take a look at what the units of those would give us. First, let's talk gradient. Gradient is going to have units of rise divided by units of run. So it's going to have units of kilogram meter per second divided by units of seconds. So for number 6, gradient units are rise divided by run. Our rise, between 2 points on this graph, right? If we were to take a look at 2 different points on the graph, we could say that our rise is going to be some number of, how much has the y-axis value changed, and the y-axis is measured in kilogram meters per second. So our rise units are going to be kilogram times meter times seconds to the -1 divided by our run units. And our run is going to say, how much has the x-axis value changed in that time? And the x value is measured in seconds. So our run is going to have units of seconds. All right. So here we say our run has units of seconds. What does this simplify to? Well, it's tricky because you can't cancel this seconds and that one because this seconds is really on the bottom, right? So we could rewrite this kilograms times meters over seconds on the bottom here, and this seconds on the bottom. Or kilograms times meters times seconds to the -2. Is that unit, kilogram meter times seconds to the -2, is that unit a unit of force? And in order to answer that, we have to figure out what are these units. The Newton, what is that equal to? So let's take a look at the Newton. A Newton is a kilogram meter per second squared. Kilogram meter per second squared. This is a Newton. And so the gradient does give us a force. So the real question then is, what is the slope of this line? Well, you could use any 2 points on the line, and I have arguably the most difficult points here selected, but let me select some easier points here so that we can do this a little bit easier. There's 2 points that are quite far away. IB wants you to use points that are further than half the length of the line away for straight lines, finding the slope. And we could easily find the rise. In this case, it's 200 kilogram meter per second. And the run, in this case, my run is from 0 to 10 seconds. And we can find the slope by taking 200 kilogram meter per second divided by 10 seconds, rise over run. So the slope equals rise over run equals, my rise was 200 kilogram meters per second over my run was 10 seconds for the easy points that I picked. It doesn't matter which points you pick, so you might as well pick ones that are simple. And we have 200 divided by 10, that's 20 kilogram meters per second divided by seconds gives me a kilogram meter per second squared. That is a Newton. So the slope is 20 newtons, and that also tells us what the magnitude of the force is. C, 20 newtons. Last problem. The graph below shows the variation with time of the magnitude of the force F acting on a body moving along a straight line. The shaded area represents what? So, This is another problem where we're saying, what does the area underneath this curve represent? And the way that we answer that is with units. In other words, let's figure out what would the units of one grid box or one small piece of area under this curve. Well, if the y-axis measures force, then the units of this side is going to be the units of force. Units of force is a Newton. That's a kilogram meter per second squared. So we could write that this would be in units of newtons, or we could write in units of kilogram meter per second squared. The base of this square is going to be a time, which we use seconds to represent. So we have seconds is the units of the base. Now the question is, the area of this is going to be base times height, or units of something in units of seconds times something in units of kilogram meter per second squared. What would that give us? So number 7, the units of area are given by base times height, which has units of our base is in seconds, times our height is in kilogram meter per second squared. What is that equal to? Well, a second times a kilogram meter per second squared. This second cancels with one of these seconds. We end up with a kilogram meter per second. It's interesting. Kilogram meter per second does not show up on this table, but had you done this assignment, you have already written in the one missing quantity, that is momentum, at the bottom of this table. It asks you to do it on problem 15. And the units of momentum are the kilogram meter per second. And so we could say that this unit is really a unit of momentum. So that is a measure of momentum. And then we could say that it's not work, it's not kinetic energy or some kind of energy, it's not velocity, it has to be momentum, because the units of it match the units of momentum. So 7, the answer is C, momentum. All right, great. That's the end of this video.